Well, thanks everybody for coming. I come at this from a very different direction. I'm a software engineer, and the way I've coded over the years and the projects that I've been involved with and the clients that I've worked with have always needed, from one reason or another, to have some degree of knowledge about exactly what's going on underneath the covers. So I've kind of, over the years, gotten more or less involved depending on the timescale in expert systems and artificial intelligence. So today, because I kind of stepped in at the last minute, I didn't quite know where to pitch this. So I'm going to talk about hardware optimization and the way that it relates to GPUs, FPGAs. I'll relate my own experience with FPGAs, and then we'll talk a little bit about ASICs and so on. If you want to sort of like go faster in different areas, because some of this is taken from introductory content that I've given to clients and developers as part of my job, which I'll talk a little bit about. But if you want me to go faster or slower and dive into or get out from, please just talk to me. I do like to have interactive sessions because I think there's a lot of value in the exchange and hearing from each other as well. So we're going to talk a bit about parallelism. Back in the day when I started doing this stuff, everything was within constrained environments of execution and with memory. And I'll talk about why I think that's still important today. And the obvious things about the optimization of latency and throughput. Yeah, we'll get to the how we get things done. So who the hell am I? That's me. I work for ThoughtWorks. Has anybody heard of ThoughtWorks? So I'm one of the heads of technology and also one of their CTOs. So sort of geographically, I look after Europe and whatever else is kind of going on at the time. I started coding for money in 1985. As most people that do, they're sort of like, so I studied when I was 8. I didn't. I was doing much more interesting things when I was 8. And I've worked in computer-aided drafting, a few other product companies, and touched on sort of aerospace. But basically, I've spent most of my time in investment banking. Then a chunk of time in broadcast TV. And I've gone in and out of various bits, including expert systems. But for the majority of my career, probably since 92 or so, I've been a consultant in one form or another. So I've worked as a contractor, worked for consulting companies, and I've spent the last 6 years at ThoughtWorks. But most importantly, I see myself as a software engineer. My interest and the common terms that people use these days about passion is coding. I tend to get involved in all sorts of things these days. Like you can see me talking about privacy and regulatory compliance and GDPR and all sorts of other things that are a million miles away from this stuff. So my job is nothing if not a bit varied. So the interesting thing about AI to me is how it's been part of our culture over the years, really since science fiction started writing, that there's a few things within sort of IT, if you like, that have captured the public imagination, and certainly AI is one of those things. And why do we need to worry about actually what's going on under the hood? When we saw, it's quite interesting when I came in about 1:30 and haven't had the opportunity to see the talks yesterday and this morning. So I was kind of wondering where to pitch this. And it strikes me as interesting how we can still work within an environment where you absolutely have to worry about what's going on under the hood, right deep down. And there's an awful lot of use of analytics of different sorts that makes no assumption and doesn't even know or care about what's going on. And we've worked through differing levels of abstraction, and we'll touch on that. So I kind of wanted to do that in terms of my own life almost, and through the tuning sort of pathway that I've had to work with from the growth of the CPU and how it's evolved and how it's tuned to this day, and how that relates to the rise of GPUs and then more specialized hardware. So obviously we've heard a lot of people talk about the differing types of hardware. You know, you've got the FPGA, you've got a TPU in the middle, a crypto antminer there for the sort of classics ASICs machine that people tend to think about in this day and age. I've actually had 2 of those. I got involved in mining Bitcoin for fun. I made, I think, 24 Bitcoin, and then sold it way before it got valuable. But I was interested in it from a sort of software engineering point of view, and actually trying to work out how the hell to get those things to work. But then we're more familiar with, you know, various forms of CPU and generalized computing. And Nicholas Wirth, anyone who's been in sort of computer science education knows, or probably of a certain age, will be familiar with Pascal. And the writer of Pascal, Nicholas Wirth, came out with this comment: software is getting slower more rapidly than hardware becomes faster. And we've gone through ups and downs in, if you're a generalist software engineer, we've worked with different levels of abstraction. So in the 80s, we were sort of C++ programmers. Then 96, Java came along. And after Java, we've gone through different variations of JVM languages, for example. And Ruby on Rails, the sort of the big exodus that everybody expected away from Java that really didn't. But the idea for many people that came up and trained through those environments, they have no idea what's going on down under the covers. And to some extent, with the JVM, if you really want to make that work and make it more aligned to the hardware, you have to get a bit more involved. But it's a completely different thing. So a lot of people I speak to come up with this assumption: well, can't we just depend on the cloud for everything? Can't the cloud sort of do everything for us? And they assume that when we talk about scaling, most people talk these days about microservices. And my company's heavily associated with the microservices movement. In fact, I worked on the project that was associated with the beginning of microservices. I worked on it when it was in a tailspin at the end. And I have no association, I have no rights or credits to the microservices movement. But many people, when they start to think about microservices, they start to think about distributed systems and all of the distributed systems rules that many people who'd worked in things like RPC, for example, that had to learn the hard way. Now we've got a generation of people that have no idea about that. They talk about microservices being interconnected, and they have no idea what happens when you get deep layers of errors and cascading of errors and failover and availability. They just rely on the fabric and Amazon and AWS and so on to solve those problems for them. So we sort of have this problem about people's perception and the abstraction, and then we have the need to actually execute these things at scale. So we then came to 1994, and couldn't we solve a lot of the problems with big data, the whole MapReduce paper, and then into its usage on Hadoop and now Spark? Very popular frameworks, very useful frameworks. But again, the generation of developers that work on these environments have no real concept about the amount of data movement that occurs, the amount of storage that needs to occur in between each shuffling of the layers, and the amount of times you have to rerun that entire thing. Of course, you have to do that because the whole big data thing is big. So it's designed for problems of a certain scale that the world has not seen before. And we've all heard and read the reports on the amount of data and devices and generation of events and so on. But the problem with this is that there's a lot of waste, awful lot of waste in those environments. And to be able to do the things that we need to do, we need to learn some lessons about how other problem spaces have grown over time. You can do it? There we go. So look at the crypto movement. Cryptography and the Bitcoin blockchain is one example of one problem. A lot of people tend to think, oh, well, look at what the blockchain does and how can we apply it to these types of things. Completely different question, different argument. But the Bitcoin blockchain, a bit difficult to say after a few beers, is one example of an algorithm, the proof of work algorithm, and how it works, and why, when Bitcoin started, when I started coding Bitcoin in 2009, I was just coding it in C on my machine that I have at home. I've got a multi-socket, multi-core, or had machine at the time. And I was trying to rip as fast as I could with that machine directly. And then my performance in terms of the number of gigahashes that I was being able to calculate was being ripped by other people that had investment in FPGAs at the time. And the reason is because what happened is we took generalized hardware, and then we took a problem, and then people started creating hardware solutions that were tuned just to that problem. That's all it could do. So then we went from what an FPGA does, which we'll talk a little bit about later, into a application-specific integrated circuit, an ASIC, that is only designed for that purpose. So FPGAs, the whole idea, it's a specific piece of hardware, but it's to a degree programmable, whereas an ASIC is burnt. So that's it, that's what it does, and it does it very well indeed. So this whole process of going from isolation of a problem, from a generalized computer that's optimized, through to some form of other type of more specific execution unit. GPUs can come into this, then FPGAs and ASICs. A lot of people think that's the progression that we've got to learn from in terms of other problem spaces. Now, I nicked this from NVIDIA, but I think given this audience, this is sort of introductory material, you don't need to know this. Machine learning is obviously a much bigger sphere. Now, I'm really interested in this from a sort of an algorithmic complexity point of view. If somebody comes to me and says, I want to run these particular chain of models, then what interests me is how well they work. How do I get the data into that model? How does it produce its outputs? How do I link those up to the inputs for the next model, and so on. So from a machine learning point of view, I'm looking at the asymptotic complexity of a particular algorithm. For deep learning, it's neural networks. So we have an idea about the different types of neural networks and how they work, and there's obviously an awful lot of interest within that sphere at the moment, so we'll look at that a bit later. Machine learning is a bit different because machine learning is a massive wide area. So to be able to tune a problem that's geared towards tensor analysis is a more constrained problem algorithmically than machine learning is, because there's a lot of different things that we can call machine learning. In fact, there is a whole suite of things that you could say, well, it's anything to do with statistics and analytics, right from sort of like weighted sum averages and things, right the way up to sort of prescriptive analytics, which should tell you which is the best way to do something, to run your company. So you have to understand kind of how constrained your environment or your problem space is. So in a sense, we can see from this is just a list of the way the industry's gone. All the big players, you'd expect companies like Intel, and Intel are obviously a really big player in this space, but you'd think that they would be in your top 4 or 5 companies, and you wouldn't expect to maybe see Facebook in there. But the reason why these companies are constructed like this is because they've got your data, and there are all sorts of issues around privacy, ethics, and the way that they want to monetize your data. So you look at the number of acquisitions, that's the list of acquisitions that companies have made. We're in an arms race. We're totally in an arms race. And there will be a race to the bottom in terms of pricing for a while until domination has occurred. This is classic sort of economic monopoly that people are currently fighting for. Yet, AI, if anyone remembers Omni magazine back in the day, it's science fiction. It has this kind of like mystique around it and this kind of cultural identity that enables it to somehow get away with it's going to be this wonderful thing, it's going to solve all ills, it's going to find cures for cancer, it's going to self-replicate, and it's going to dominate humanity. And films have been in this all the way through since the 40s. I had a great slide in here, but I realised it wasn't that applicable by the day the Earth stood still with a huge robot. And in 1940, I didn't realise that Isaac Asimov wrote this in 1940. You know, the sort of the three laws of robotics that came up in the film I, Robot about 10 years ago, or whatever it was. Then in 1953, we looked at the specific, this is a specific piece of hardware to solve one particular problem. Alan Turing, the father of modern computing, he went on to devise the multi-purpose computer, the father of modern computing. His first work helped to shorten the war by a number of years by being able to, that machine was able to find the crypto keys that were used to decode the Enigma messages. So you had to have a machine. Ooh, what was that? But we've got an really early example of one particular machine for a particular problem. Then if we move forward a little bit in time, you know, again, artificial intelligence within within the outside world and within the psyche. We've got Lisp. I kind of like this. If anyone's ever worked in Lisp, this will appeal, especially the diagram on the right. At the point where Lisp was formulated, abstraction had got higher. We had languages at the time like Fortran and COBOL. COBOL was an information systems language. Fortran, formula translation, maths and physics engines were being built with that. And high levels of abstractions, the lambda calculus and predicate logic were being utilized to try and think about modeling problems. I spent some time in the 80s with those very books working on a deductive database in Prolog. So at the end of 1999, you'll see where I'm going with this in a sec, the US government issued this book, or booklet, talking about the level of investment and how they were responsible for the upswing in technology and the speed of innovation. It was all because of them. So if you sort of like think of this time scale, you've had these sort of efforts that have been involved, the public psyche, sci-fi, it's been involved in everybody's thinking, especially in the film world, the film and media world. And it's been funded up to a point. So 2001, this is this film, AI, the Steven Spielberg film. But what happened, 2001, AI sort of died. In fact, it had died for a number of years up to that point. And the reason was that it just wasn't working well enough. The models that were being constructed, I mean, I was working in expert systems at the time, and it just wasn't accurate enough, and it was just taking too long to do anything. And I thought it was great. I couldn't understand what everyone was worried about, but it was just that we can't do the calculations quick enough. We can't do them cheaply enough because the amount of calculations that have to be done are just too expensive. They take too much power. We can't do enough calculations, so we can't handle the scale, the exponential growth of data, and we can't actually do the calculations that we need to do. If you've worked in HPC, you'll have to construct a dependency graph for the calculation that you need to do and the interrelationships between the precedence of the calculation. And you've got to split it up, and you've got to work out how to execute as much of that in parallel as you possibly can and use message passing to actually implement that. And some problems just don't fit that very well. They're complicated problems. This is not easy. And one of the big problems that still pervades to this day is that to do anything takes too long. So therefore, if you're working with a researcher, if you're working with a statistical sample, and you're working with a researcher, then it might be okay that you can go away and do something and come back and say, hey, have a look at this. But the iterations when you're using large scales of data just don't work. It's just not practical still. We can't keep data local enough. I'll come back to that in a minute. We have always been at the edge of existing technology capability. We're trying to squeeze as much as we possibly can, and we're trying to create specific pieces of hardware to do certain types of calculations. So it's not true that a GPU or TPU or an FPGA can be the answer to any machine learning problem. you have to segment, and it has to be solvable for the particular problem sets that you're working with. And not all problems can be divided so easily. So Moore's law, it's a bit of a classic one. Many people argue whether Moore's law still exists, and this is a slightly older slide, but it doesn't matter. So in the mid-60s, the law that's attributed to this guy talks about the doubling of transistors about every 18 months. And you can see from this that this is still true. And this is still true to this day. So in that sense, Moore's law is still carrying on. But we know that clock speed plateaued away actually about 10 or 12 years ago, and that's still true. This is sort of 2011, 12. And that's still true, still plateaued off. So the classic answer to that, oh my God, it's Moore's law, that's a problem, is, oh, well, we've moved into a multi-core world. Well, we're actually in a symmetrical multiprocessing world before that. We were already working with multi-socket boards, and we were already working with clusters with high-speed interconnects. So you can see here that actually what's happened is that we've slowed down in terms of this is a normalized graph against the VAX in 1978. So you look right the way down here, you can see that actually what we were doing is we were increasing 25% a year, then we were moving 52% a year, then it flattened off right the way back so it flattened off, 2003. Exactly correlates with the previous graph, and they're from different sources. So what do we need for success? Somehow, we've got to get as much raw compute power as we possibly can. We have to achieve locality. We need high-speed interconnects. So anything that communicates with anything else needs to be done as high speed as possible. The difficulty is that physics is against us in many ways. We need looser memory models. Does anybody, are you aware of programming with different memory model types? Right, okay, cool, I'm getting a few nods. We need a fully utilized fabric. So whatever it is that you're executing on, whether it's a machine, whether it's a cluster of machines, or whether it's a network, or whether you're utilizing this within a service within the cloud, you need to be running at full bore the whole time. And you need advanced metrics to be able to work out that you're actually utilizing your bang for buck correctly. If you've ever tried to optimize hardware execution with tools like vTune, you'll know how painful that actually is. So this is a little bit of fun. This is a little bit old, so the scale is, it's still, the relative scale is still right, but we actually execute in clock cycles in less than 3 nanoseconds now, 0.3 nanoseconds. So, sorry, this is not my clicker, beg your pardon. Right, so if you just take the scale that if we do one CPU cycle, let's call that 1 second. Let's just call it a second, just because seconds are easiest for us to get our heads around. So if we then go the relative scale, we go to a level 1 cache access from there. That's 3x just to move to your first level of cache. If you want to go to level 2 cache, that's 3 times again. That's 9 seconds, okay? Then you want to go to level 3, it's 43 seconds. So that's a big jump there. So the cost of execution is incredibly high. So you want to go to main memory, 6 minutes in this relative count, okay? 6 minutes when going from just 3x to go to level 1 cache. 6 minutes, huge. Okay, you get what I'm trying to do here. I'm just getting a couple of critical looks, yeah? So if we want to go to like solid state flash memory that's a cache on an SSD, that's 2 to 6 days. Go to old school rotational disks, it's 1 to 12 months. The 1 month would be if the disks are already spinning and so on, and possibly if you've got a RAID cache in front of it. Then you get into sort of some of these other things that are probably less relevant to this discussion, but like internet communications, 4 years from San Francisco to New York. And then you get down to a physical system reboot, which is 32,000 years. But the cost of I/O is probably one of the biggest factors that will affect any success of anything that you do. So if we go back to von Neumann and have a look at the very simple model that he devised in 1945, And what's actually been done with that ever since? So what's wrong with the CPU? We've squeezed the nuts out of CPUs for years. So why can't we just solve these problems with regular programming languages and that level of abstraction that the compilers give us? Because it does speculative execution, it prefetches memory, we've got the cache hierarchy that we just discussed, we can do warming of virtual memory TLB addressing, we can do all sorts of things that like optimize the arithmetic logic unit. We have multi-cores with bus interconnects that are higher speed. We've got multi-cores, so on the multi-sockets we can have multi-cores. We can do branch prediction. We can do pipelining, instruction parallelism, so we're actually fetching and we're doing loads and stores in parallel. The memory models and out-of-order execution. I mean, for those that nodded to me about memory models a few seconds ago, for the others, who thought that your instructions that you sent down to your CPU were executed in order? Because they're not. There was a funny experience I had a number of years ago where the DEC alpha machines that were sort of prevalent in the, what would it have been? Would it have been the 90s? Yeah, it probably would have been. They had a very loose memory model. And Microsoft had invested heavily in the DEC alphas at the time, and they ported SQL Server to it. SQL Server is actually a great database, regardless of what anyone else tells you. I've bent the nuts off it. And it just didn't work because the cache consistency between the caches on each chip, it doesn't hold that necessarily for you. x86 has a thing called total consistency ordering, which means that when something is written to memory, it will update all the other caches and all the other cache layers, which is very coherent, but it means it's very inefficient. So it makes it much easier for you as a developer not to worry about that type of thing. So we live in this world where we have to be worrying about a constrained environment. We have to be worrying about the execution at different levels. So this brings us back to Flynn's taxonomy. Everybody knows Flynn's taxonomy, right? Did they? So, come on, everybody else, I'm getting the same nodding heads. Talk to me. This was devised in 1966, actually. An SISD, single instruction, single data stream, is kind of the single CPU. It's the traditional von Neumann model. You've got one instruction that needs to be decoded and executed, that's that. Then you look at single instruction, multiple data, you're looking at trying to say, I need to analyze this thing, but with this set of data, and that's classic sort of vectorization. So that's kind of, simplifying, but that's kind of your GPU. MISD is more about failover and disaster recovery. The only real examples, it was really only put in initially to the taxonomy to complete the analogy. MIMD, this is more about the way the Xeon Phi works as a coprocessor next to a regular GPU in terms of offloading instructions and working via a distributed memory bus. So we've had these types of parallelism for a long time, data level parallelism and task level parallelism. So we can divide those into instruction level, vector architectures, thread level parallelism, and request level parallelism. So here's the problem, right? So we kind of said when we went into that sort of multi-core jump, hey everybody, you're going to need to worry about concurrency and so on. Any Java programmers here? Okay, go and read JSR 133 and 166, but 133 first. Because that describes to you the memory model and how the memory model matches the guarantees against the hardware. And we have to now suddenly say, whoa, everybody's got to worry about this again. This is a bit of a problem. So when you're starting to worry about the way your code executes on those cores, and you're looking at the way that that code executes within a distributed environment, because maybe you're a microservices guy, maybe you've got something with a load balancer and you're splitting that information across multiple instances. Maybe that's an HPC cluster. So you've got that level of delegation, and then you've got the optimization of potentially running on multiple threads, and maybe even you're hyper-threaded within the local box. So you've got different levels of delegation that can occur. You need to worry about that. You need to worry about the message passing that occurs within that. And it's very difficult to be able to communicate at that level and then work on environments like CUDA or OpenMP. If you've worked like that, if you're a Java programmer, it doesn't really work that way. So you have to work in a slightly different way. And with everything with the law of diminishing returns, if you don't understand the way your code is executing in the wider sense, you'll run into Amdahl's law, which fundamentally just talks about the theoretical speed up, and you're limited by the sequential part of your operation. So you will fail to get past a certain point, you get a law of diminishing returns. So Amdahl's law extended. It was really designed with scalar execution in mind, and that's where CPUs have concentrated really. Even though we have things like the AVX extensions in the last few years, vectorization has really been better occupied on separate devices. So we have to try and concentrate on getting the highest amount of arithmetic intensity. So that's how do you burn your cores as high as you possibly can, keep them busy, and keep them busy in the right way, and not get them wasting any time. So consider the efficiency of your algorithm. You have to profile at different levels, and you have to profile down to hardware counters. So I'm just going to skip that. I want to get onto this because I'm going to wake you up. This is a bit of fun.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
when we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9,
8,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
I like that. When I was putting this together the other day, I was thinking, whatever happens, I'm going to get that in here. So you kind of get the idea that, like, you break up a problem. It's an embarrassingly parallel problem where the algorithm differs really only by the set of data that's applied to it. And the programming model is familiar if you're a certain type of programmer. So if you've worked with C, C++, I know that there are other languages available, as the saying goes. I know a lot of machine learning people work in Python and R. I come at this from the point of view of optimization completely. I've spent a lot of my time working with quants in investment banking. This is the way that people work in the areas that I've worked in. So just just because of time, we get an FPGA. So how do you compare that with the GPU? GPUs is a general purposely available thing. There's APIs, you can program them. It's a bit of a pain in the arse, but it's actually relatively doable. FPGAs are a completely different programming model. In fact, the programming model is very similar between an FPGA and an ASICs in that you have to work with hardware description languages like Verilog. If you've done it, then I think you need a sort of badge of honor. I survived. It's more the realms of an electrical engineer to work with clock cycles and timings. It's not something that a regular software engineer does. So thank God that some of the new abstraction levels that do exist handle some of that for us. So an ASIC, you can see there an example of VHDL. It might look like code, but believe me, when you start looking at it, it's not going to look very familiar. The thing with an ASIC is that it's a one-shot cost. It's a high upfront cost with FPGA. Sometimes there's licensing costs associated with issuing new boards and so on. This is usually a one-shot cost. You're not going to get any change out of 50 grand to do an upfront creation of one-off board. So you better get it right. So we talked a lot about TPUs, or I believe you've talked about it for a while. It's an ASIC. It's specific for the problem. It specialises on low precision. So I'll get to that in a minute. It's very programmer friendly because you've got TensorFlow and other language models are available. And the problem that it maps is the human neuron and the synapses. So we don't need to do that, and we don't need to necessarily look at that because these change all the time. Every time I look at this and I see somebody, if we look at the Microsoft figures with their FPGA stacks, and you look at what Google are doing and what they're predicting, it's like people are jockeying for position the whole time. One interesting piece has come out of the guy who's the CTO of NVIDIA, and a guy you probably would have run into if you've looked at this stuff online, a guy called Song Han. And they're talking about this efficient inference engine. Now, the reason why I thought this was interesting to bring to this, if you haven't seen it, go and have a look. Because they talk about building a specific ASIC, and the key to this, the key above all else, is that they have put a bucket load of memory as a system on a chip. So the data locality is key to them. So everything they need to do, they pull it onto chip. So if you look at the guys that designed the TPU, and you look at these people, it's interesting, it's not being done by practitioners in the field, it's being done by hardware engineers that understand machine learning to the mathematical level. These are the people that are designing the next generation of chips. So what they've done is they've taken a neural network, and they have found that when you go through the process of the training and then the inference, that you can go back over that and prune away an awful lot of the actual network. And if you retrain the network, you can still get nearly as good results. So from a computing point of view, that just means I've got a lot less calculations to do than I did. So they approach this from an optimization point of view. They then, when you have your array of weights that you need to refer to, they will then share the weights. So they use a pointer idea to actually point to the weights. Doesn't sound too outlandish. But then what they'll do is they'll take a range for the weights and they'll quantize them down. So there's less weights. So there's less nodes in the tree and there's less weights. And there's pointers to those weights. And then they'll actually compress the data. So they use Huffman encoding. So here's these ideas that have come from mainstream computing, and they're being applied to an ASIC that is designed for efficiency. It's all about throughput, it's about minimization of latency, and it's about locality. I encourage you to go and look at it because it's very interesting, but it's kind of like now. You know what I mean? It's one guy's research, and he's been sponsored by NVIDIA, so you can imagine how this is going to go in time. And it's that jockeying that they're doing. So just to finish up, I was just going to say, Intel are doing their own thing with a new Knight's Mill and the Knight's Crest offering. It's horses for courses. It's every time you look at something, they've got some compelling data that puts them at the head of the race this week. So in total closing, what are the open questions? Well, whatever your battle is, if you wait to sit in the cloud and you're prepared to pay enough, you will have access to these things. Google are being hailed, and I think they're sort of self-hailing themselves as being 7 years ahead. They're certainly not using some of the hardware. It's not quite as far ahead as in terms of generation. The actual wafer dimensions are not quite as far ahead as some of the competitors. Think about the competitors, really. The people that you need to consider, apart from Google, obviously, are Facebook and Apple, and maybe Amazon. Because they, like I said before, they have your data. They will be the people that drive the innovation because that's where the money is. Competition over pricing. Well, there will be a race to the bottom, but everything is always going to be expensive to train. Inference is a totally different thing. There's obviously, you can see segregation of hardware between inference and training. And coming back to the point of one of my company issues, continuous delivery. It's a whole talk in its own right. How do you actually get an idea from someone's head to production in an automated way? Well, when you're doing things with ASICs, that's pretty much impossible to do without simulators, and there's a gap between simulation and execution in terms of real-world results and performance. So I think that kind of brings me to the end,